On a calm winter morning, a brand-new ship decided to die. It made no sense. There was no storm, no explosion, not a single enemy in sight. And yet, there it was, happening in plain sight. January 16th, 1943, Portland Harbor, Oregon. The water was still as glass under a pale gray sky. Dock workers moved through the cold fog, their breath turning to mist as they prepared another Liberty ship for its final inspection. The vessel was the SS Schenectady, and she was a symbol of a miracle. Launched just weeks earlier, she was a product of America's industrial might. A ship built faster than anyone thought possible. But as the sun climbed over the harbor, that miracle was about to become a national nightmare. At 11:15 in the morning, a sharp crack echoed across the docks. It sounded like a rifle shot. Then another and another, until it became a chorus of tearing steel. Within seconds, the massive hull of the Schenectady began to bend, as if it were breathing. Witnesses said the deck plates rippled and then split open with a deafening roar. An invisible knife seemed to race from one end of the ship to the other, slicing through feet of solid steel. Men shouted and scrambled for safety as the vessel tore itself apart, right there at the pier. When the awful noise finally stopped, the Schenectady was no longer a ship. She was two halves of twisted metal, her back broken, her deck hanging like torn paper over the black water. How could this happen? How could a vessel, with no enemy in sight, simply tear itself in two while tied safely to a dock? Within hours, investigators swarmed the wreck. Engineers crawled across the cold, bent steel, their boots clanging in the silence. The fractures were bizarrely smooth, almost surgical, as if the metal had shattered like glass instead of tearing like steel. Theories began to fly. Was it bad welds? Cheap materials? Sabotage? A fatal design flaw? But none of them fully explained why the ship had failed so completely, so violently. And the most terrifying part was, it wasn't the first. The Schenectady was just the latest casualty in a growing and terrifying list. In the months before, other ships had met a similar fate. The SS John P. Gaines had snapped in half in calm seas off the coast of Alaska, throwing her crew into the freezing Pacific. Another ship, the tanker SS Manhattan, fractured so suddenly that her sailors abandoned ship in a panic, certain they had been torpedoed. By 1944, over 2,000 ships had reported serious structural failures. 19 of them broke completely in two. 3 simply vanished at sea, leaving nothing behind but an oil slick and a ghost story. These weren't losses from enemy action. These ships were destroying themselves. Sailors began to fear the very vessels that were meant to be their lifeline. Some refused to sleep below deck, terrified of being trapped if the hull gave way in the night. They spoke of hearing eerie pings echoing through the steel, a sound like glass under strain, just hours before a disaster. Engineers dismissed these stories as superstition, but the superstitions were multiplying because the cracks were real. What were these sounds? Was it just the groaning of a working ship, or was the steel itself sending out a warning that no one understood? To understand the scale of this crisis, you have to understand what the Liberty ship represented. After Pearl Harbor, America faced an impossible challenge. It needed to supply a war across 2 oceans, and that required cargo ships, hundreds of them. Traditional shipbuilding was far too slow. It could take 8 months to build a single vessel. America didn't have that kind of time. So, the industrialist Henry Kaiser, a man who had built dams but never a ship, made a revolutionary promise. He would mass-produce them, like cars rolling off an assembly line, and at first, his idea worked beyond anyone's wildest dreams. By late 1942, his shipyards were launching a new Liberty ship on average every 42 days. Propaganda films celebrated this miracle of American industry. Women welders, Rosie the Riveters in a new role, replaced the men who had gone to war, their torches lighting up the shipyards day and night. The slogan was everywhere: "Speed wins wars." And for a moment it seemed true. But that speed came with a hidden cost, one that no one yet understood. The problem was the cold. In the frozen waters of the North Atlantic, where temperatures could drop below 40 degrees Fahrenheit, the Liberty ships began to fail in strange ways. The welded hulls, which saved so much time in production, were behaving differently than the old riveted ones. Before, a small crack might be stopped at a seam. Now, with hulls made of continuous sheets of welded steel, a tiny crack could race unchecked across the entire ship, devouring it in seconds. The very process that made the ships fast to build was also making them fatally brittle. By the end of 1943, the program that was once America's greatest triumph was turning into a national embarrassment. Each broken ship wasn't just a lost vessel. It was a severed artery in the war effort. The press called it the mystery of the breaking ships. In Washington, committees demanded answers. Naval architects blamed the welders. The welders blamed the steel mills. The steel mills blamed the designers. And while everyone argued, more ships cracked apart in the dark. The miracle that was supposed to carry America to victory was breaking under the weight of its own success. And in a California shipyard, under the flicker of welding torches, a woman no one had ever heard of was about to see the one simple truth that all the experts had missed. The miracle that was now cracking apart had begun with a promise from a man who refused to believe in the word impossible. When the government approached Henry Kaiser about building cargo ships in 1941, the established shipbuilding world laughed. Kaiser was a dam builder, a man who poured concrete, not a naval architect who riveted steel. But he saw things differently. "We'll build them like cars," he told reporters, "factories on the water." And when America's entry into the war turned the oceans into a battlefield, he delivered on that promise with breathtaking speed. His shipyards in California and Oregon looked nothing like the shipyards of the past. The slow, rhythmic hammering of riveting teams was gone. In its place was a storm of electric sparks and motion. Giant prefabricated sections of hulls were built in enormous sheds, ready to be welded together like massive puzzle pieces. Conveyor belts carried steel plates directly to assembly lines. Floodlights turned midnight into noon. The pace was relentless. A ship that once took 8 months to build was now sliding into the water in 40 days or less. One vessel, the SS Robert E. Peary, was assembled from its first steel plate to its final launch in just 4 days, 15 hours, and 26 minutes. The newspapers called it a miracle. But every miracle has a flaw hidden beneath the glory. The Liberty ship was an engineering compromise, a vessel designed for speed of construction, not for a long life at sea. It only had to survive the war. The old way, riveting, took time and precision, but it also created natural safety barriers. The overlapping plates and thousands of bolts meant that if a crack formed, it would usually stop at the next seam. Welding, however, was a different story. It was faster, saved weight, and allowed for simpler construction. But it also introduced new kinds of stress that no one at the time fully understood. Unlike riveted joints, welded seams created a continuous sheet of metal from the bow to the stern. This unbroken surface was incredibly strong when compressed, but it was terrifyingly fragile when pulled into tension. In the mild climate of California, where the ships were launched, this problem was invisible. But in the frigid North Atlantic, everything changed. At temperatures near freezing, the steel lost its ability to bend and flex. It became brittle. A small imperfection, A sharp corner on a hatch, a tiny flaw in a weld, could become the starting point of a catastrophe. And the way Kaiser's shipyards were building these vessels made those flaws inevitable. The workforce was new, filled with women who had never held a welding torch before. They were fast, they were precise, and they were proud. Propaganda posters celebrated them, their faces glowing blue in the light of their work. On every bulletin board, the same slogan was posted: "Speed is the best armor." It was the gospel of the war economy. Speed meant victory. Speed meant freedom. But speed also meant mistakes. Each Liberty ship was pieced together from hundreds of welded sections, but no one had established a standard sequence for how to weld them. Crews often ran long seams from one end of a plate to the other in a single, fast pass. As the molten metal cooled, it contracted, pulling on the surrounding steel. This pull created a powerful tension that became locked deep inside the structure. Every finished weld trapped a little more strain. By the time a ship was complete, its hull was coiled with millions of pounds of invisible tension, like a tightly wound spring, just waiting for the right conditions to snap. Why did the engineers, with all their slide rules and calculations, miss this? Was it a simple oversight, or was the relentless pressure for production so intense that it created a kind of collective blindness, where small warnings were ignored in the name of the greater goal? In 1942, no one saw it that way. To the public, Kaiser's shipyards were monuments to American ingenuity. Newsreels showed smiling women in coveralls, sparks flying as swing music played in the background. When President Roosevelt visited, he called it proof that democracy could outproduce tyranny. And then the strange reports began. At first, they were just thin, hairline cracks near deck hatches. The engineers dismissed them as surface imperfections, but the cracks kept growing. Some ships reported hearing sudden pops during their voyages, the sound of steel releasing its tension. In late 1942, entire sections of hulls began to split apart. The failures came without warning, without storms, without enemy fire. Naval investigators swarmed the yards, blaming unskilled labor, bad welding rods, or poor supervision. Orders were given to double-check every seam, to retrain workers, to reinforce the hulls. But nothing seemed to stop the failures. Metallurgists analyzed samples of the broken steel and found nothing wrong with it. The numbers all said the ships should have been strong, yet they weren't. Behind the official reports, a quiet fear was spreading. In letters home, sailors wrote about the cursed ships. Dock workers whispered that the Liberty hulls were haunted. The Maritime Commission began quietly altering designs, adding reinforcing straps, and even experimenting with riveted joints again. But the pace of production could not slow down. America was fighting on two fronts. The Allies needed ships, not theories. And so, the experts kept looking for answers in their laboratories and their blueprints, never imagining the solution was already waiting on the shipyard floor, in the hands of someone who simply paid attention. Long before history would remember her name, Bessie Hamill was just another face in a sea of overalls and sparks. She worked the graveyard shift at Richmond Shipyard No. 3, from 10 at night until the sky over San Francisco Bay began to glow a pale gray. The air was always thick with smoke, heavy with the scent of molten metal. To most, the noise and the heat were just part of the job, an industrial symphony playing to the rhythm of war. But to Bessie, the shipyard was alive, and the steel was trying to say something. She had been there for 8 months, long enough to know the sound of a good weld from a bad one. A clean, balanced seam hummed with a steady pitch, but a stressed joint rang higher, sharper, like a violin string pulled too tight. At first, she tried to ignore it. The foreman said small distortions were normal, just part of the process, but she couldn't shake the feeling that something was fundamentally wrong. The massive steel plates they welded each night, some 20 feet long and an inch thick, were warping in strange patterns. When they cooled, they didn't lie flat. They bowed slightly as if the metal itself were fighting against its own shape. Most welders learned to compensate for this with brute force. They hammered the plates into place, clamped them down harder, and welded faster. Bessie did the opposite. She slowed down, and she watched. Each time she laid down a seam of molten steel, she marked how the plate moved in response. She began keeping a small notebook in her lunch pail, sketching crude diagrams of how the plates twisted and buckled. She noted the sequence of welds, the pattern of heat, and the order her team followed. And slowly, she began to see a pattern emerging. One that had nothing to do with bad steel or unskilled hands. Every shift followed the same routine. Welders started at the edges of a plate and worked their way toward the center, or they ran long, continuous seams in a straight line from one end to the other. Bessie realized that with each pass, the cooling weld contracted, pulling the surrounding metal tighter and tighter. The tension had nowhere to go. It was being locked into the very structure of the ship. By the time the next seam was added, the stress was already trapped. It was like trying to build a house by nailing down the floorboards from the outside in. The center would inevitably bulge and buckle. She tried to explain what she was seeing to her foreman. He laughed. "The engineers know what they're doing," he told her. "You just run your torch and keep it straight." When she persisted, he pointed to her quota, 20 feet of welded seam per hour. There was no time for theories, but Bessie couldn't unsee what she had seen. The steel was talking to her, and she felt like she was the only one listening. The more she observed, the more she realized how blind the whole process had become. Welders were rewarded for speed, not for precision. Supervisors timed each job with a stopwatch, not with an eye for stress distribution. The blueprints handed down from the engineering office showed where to weld, but not how or in what order. Was it possible that the people designing these enormous ships had never stood under one as it was being built? Had they never felt the plates vibrate as they cooled, or heard the sharp pings of metal under tension? They worked from numbers on a page. She worked from sound, from heat, and from instinct. One night, after her shift ended, she stayed behind in the yard. The floor was littered with scrap steel, discarded sections, and test pieces. She gathered a few and began her own quiet experiment. She welded them together in different sequences: edge to center, center to edge, alternating sides. When the pieces cooled, she measured their curvature with a straight edge. The results were unmistakable. The plates welded the standard way, from the edges first, bent upward like warped wood. The plates she welded from the center outward stayed perfectly flat. The next morning, she showed her samples to the foreman. He glanced at them, shrugged, and walked away. "You're a welder, not an engineer," he said dismissively. "Don't waste company material." But Bessie wasn't done. She spent her weekends running her own tests, marking the temperature drops between passes with chalk, noting how stress built up near corners and openings. She became certain of it. The problem wasn't the material, it was the sequence. The engineers had designed a system that guaranteed internal tension in every single ship they built. Word of her experiments began to spread among the night shift workers. Some thought she was crazy, wasting her time, but others quietly agreed. "Those plates are fighting back," one welder told her. "I've seen them pop like rifle shots." Yet no one dared question management. In the midst of war, production was patriotism. Delay was seen as disloyalty. Still, she couldn't let it go. Every time she read a headline about another ship cracking, She saw the faces of the men and women who had welded it, the thousands of hours they had spent under a rain of fire and smoke. It wasn't their fault. It was the process. And if she didn't say something, who would? So, in November of 1943, she did the unthinkable. She requested an official meeting with her supervisors to challenge the engineering department's procedures. It was a move that could have gotten her fired. When they asked what the meeting was about, she wrote a single, bold line on the request form: stress from improper welding sequence causing hull failure. The supervisors arrived expecting a routine complaint. What they got was a demonstration that would begin to unravel the entire mystery of the breaking ships. By late November 1943, quiet rumors were spreading across the Richmond shipyards. Someone on the night shift, a woman no one had heard of, was challenging the official welding procedures. Supervisors called it a distraction. Engineers dismissed it as shop floor gossip. But to the men running Henry Kaiser's industrial empire, the claim sounded utterly absurd. How could a single welder with a torch claim to see what the finest metallurgists and naval architects in the country had missed? Washington had held hearings, universities had written papers, and yet the ships kept breaking. The supervisors who met with Bessie arrived with skepticism etched on their faces. But then she laid her test plates on the table. She didn't use equations or technical jargon. She used the simple language of someone who had lived inside the problem. She explained what she had seen, how the heat moved through the steel, how the contraction of each cooling seam built up tension that had nowhere to escape. She showed them how a different order, starting in the center and alternating sides, allowed that stress to release outward, toward the edges. They listened politely, but dismissed her. One man called her theory impractical. Another said the distortion simply came from cheap steel. But one supervisor, an older man named Charles Horton, lingered after the others had left. He had been in the shipbuilding business long enough to know that sometimes the smallest details made the biggest difference. He didn't dismiss her. He asked to see her weld. That night, Horton stood beside Bessie as she worked. He watched how the steel plate shifted under her torch. He saw how she paused between passes, letting the metal relax and cool evenly, instead of rushing to meet a quota. When the section was finished, it lay perfectly flat on the workbench, not curled upward like the others. Horton said nothing for a long moment. Then, he spoke two quiet words that would change everything. Do that again. It was the beginning of an experiment that would rewrite the rules of modern shipbuilding. Horton ordered a controlled test, tucked away in a corner of the yard, out of sight from the main production lines. Bessie and a small team worked with two identical steel panels. One was welded using the standard method, edges first, long continuous seams, fast passes. The other followed her sequence: start in the center, alternate sides, and weld outward in balanced sections, never letting any one area overheat. The difference was visible before the welds had even cooled. The standard plate twisted upward, its edges buckling. Bessie's plate stayed flat. They repeated the test with thicker plates and more complex joints. Each time, the results were the same. Within a week, the yard's metallurgists were brought in. They installed strain gauges to measure the invisible tension locked into the steel as it cooled. When the readings came back, the numbers stunned everyone in the room. The traditional welding sequence left stress concentrations of over 30,000 pounds per square inch near the corners of hatches and other openings. Bessie's sequence distributed that stress evenly, rarely exceeding 12,000 pounds per square inch. One young engineer looked at the printout and whispered, "That's impossible." Horton, watching over his shoulder, simply replied, "It's happening anyway." But what if this was just a fluke? How could they be sure this wasn't just an isolated case, a strange anomaly that wouldn't apply to the colossal scale of an entire ship. This unresolved question hung in the air, a shadow of doubt over the promising results. Word of the experiment reached Henry Kaiser's office. For months, he had been battling political pressure over the failing Liberty ships. Congress wanted scapegoats. The Maritime Commission wanted answers. Now, in a single test bay, an untrained welder had provided both a problem and a potential solution. Kaiser requested a full briefing. Bessie's sample plates were brought to the main yard for a formal demonstration. This time, metallurgists from the University of California were present. They examined the plates under magnification, measuring stress patterns and looking for the tiny microfractures that were the seeds of disaster. When they applied pressure tests, the standard welds began to crack along the same familiar lines that had doomed ships at sea. The welds, made with Bessie's ridiculous method, held firm. That night, Kaiser sat in his office, surrounded by reports and production schedules. Stopping the assembly line now would be a monumental decision. 90,000 workers, running in 24-hour shifts, all organized around the principle of speed. Changing the welding sequence meant retraining every single welder, rewriting every manual, redesigning every section of every ship. It would slow down production at the very moment the Navy was demanding more ships for the coming invasions in Europe and the Pacific. But the data didn't lie. The Liberty ship failures were not random acts of bad luck. They were systematic, built into the very process of their creation. Kaiser did not hesitate for long. He gave the order, stop the line, start again, retrain them all. For a man who had built his reputation on speed, it was the most radical decision he could have made. Overnight, his massive shipyards transformed from assembly lines into classrooms. Experienced welders were pulled from their stations to become instructors. Each one was handed a new set of diagrams, Bessie's diagrams, showing how to sequence welds from the center outward, alternating sides, never running a continuous seam longer than 4 feet without a break. By every industrial measure, it was an act of madness. But it was the only way to stop building ships that were destined to break. The ridiculous idea had just become company policy. Henry Kaiser's gamble to halt production was, at first, a public relations disaster. Reporters mocked him. Politicians in Washington called it industrial suicide. The Navy fretted about the lost tonnage, with Allied offensives in Europe just months away. But Kaiser didn't flinch. He walked the shipyard floors, telling his supervisors, "Speed without strength is nothing. We're not building coffins. We're building lifelines." Overnight, the rhythm of the shipyards changed. In every shed, new posters appeared with a simple slogan, "Center out, never in." Each welder, from the newest hire to the most seasoned veteran, received a laminated card with numbered diagrams showing the new weld sequences for their assigned sections. Before striking the first arc of a torch, they had to trace the sequence with a gloved finger. Instructors, including Bessie Hamill herself, now reluctantly promoted to a trainer, walked the long rows of workers, watching their timing, checking the heat, and ensuring that each plate was allowed to cool evenly before the next pass. For every 10 welds, a section was moved to a massive stress relief oven, where it was heated to over 1100 degrees Fahrenheit, then allowed to cool slowly overnight, releasing any remaining tension. What had once been a frantic race against the clock became a deliberate choreography of precision. At first, the process seemed painfully slow. Production dropped by nearly 30% in the first week. Ships that had once been launched in 42 days now took almost twice that long. Schedules fell behind, and supplies of steel stacked up in the rail yards. Skeptics, inside and outside the company, whispered that Kaiser had lost his touch, that his miracle had been a fluke all along. But then, something remarkable began to happen. The errors vanished. Hull sections that had routinely required hours of rework, grinding, hammering, and rewelding were now fitting together perfectly on the first try. The weld rejection rate, once as high as 15%, dropped to less than 3%. Every completed joint passed inspection. Engineers finally began to understand the physics behind the change. Steel wasn't just a solid material, it was a crystalline structure. When welders ran a long, continuous line of molten metal, that superheated zone expanded rapidly against the surrounding cold steel, creating immense tension. When the weld cooled, that tension remained locked inside, an invisible time bomb. In the warm Pacific, the steel could often absorb it, but in the freezing Atlantic, the steel became brittle, and a tiny crack at a hatch corner could trigger a chain reaction, traveling the length of a hull at nearly the speed of sound. Bessey's method was elegant and simple. It let the steel breathe. Welding from the center outward allowed the metal to release its stress gradually toward the edges. By December of 1943, the first full-scale hull section built with the new procedure was complete. When the test team applied stress loads simulating rough Atlantic seas, the section held perfectly. The engineers were forced to admit it. The welder's ridiculous idea worked. This success led Kaiser to his next revolutionary decision. He ordered a complete redesign for his next generation of ships, the Victory class. They would incorporate every lesson learned from the Liberty ship failures. Square hatch corners, which acted as stress amplifiers, were replaced with rounded ones. The hulls would be built in smaller modular sections to allow even more precise control over the welding sequence. Even the steel itself was changed to a refined alloy with more manganese and a trace of nickel to maintain its toughness in cold water. But a question remained. Could this new, slower, more deliberate method ever match the incredible production speeds of the early war years? Was it possible to build both strong and fast? The answer came on May 12, 1944. At Richmond Yard No. 2, 17 massive prefabricated modules, representing nearly 85% of a completed hull, were aligned and lowered into place. Sparks flew as hundreds of welders began connecting the modules, each following the same center-out sequence. The entire operation lasted just 11 hours. Over the next 5 days, the yard became a ballet of coordination. Electricians ran cables through pre-drilled conduits. Pipe fitters installed steam lines that were already measured and tagged. The engine, tested off-site, was lowered directly into place, its mounts aligning perfectly on the first try. There were no last-minute corrections, no warped plates, no emergency rewelds. On June 27, 1944, the hull of the SS Benjamin Warner slid into the water. 2 days later, it completed its sea trials without a single stress crack. From the first steel plate to a fully tested ship in just 5 days and 11 hours. It was a new record, not of reckless speed, but of perfection through precision. Kaiser's team called it the 5-day miracle. Washington called off its investigations. The Maritime Commission ordered 500 more Victory ships to be built using the exact same model. The redemption of patience had proven that discipline could outperform desperation. And in the Richmond Yard, someone painted a new phrase on the wall above the main gate. It wasn't a slogan. It was a truth learned the hard way. We slowed down to win. When the first Victory ships began crossing the Atlantic in late 1944, they carried more than just cargo. They carried proof that the invisible science of stress, heat, and human observation could change the course of a war. For the first time, engineers could explain in numbers why the new ships held together where the old ones had failed. The breakthrough began with the steel itself. The Liberty ships were made from a standard alloy that performed well in mild climates, but became dangerously brittle in the cold. Below 40 degrees Fahrenheit, the steel's internal structure would change, behaving less like metal and more like glass. A tiny flaw could trigger a fracture that would race through the hull. To solve this, metallurgists designed a new alloy known as killed steel. By adding aluminum during the smelting process, they removed dissolved oxygen, preventing tiny gas bubbles that weakened the structure. A trace of nickel was also added to increase toughness in low temperatures. This new steel's breaking point dropped from a dangerous 40 degrees all the way down to just 5 degrees Fahrenheit, a difference that meant survival in the freezing North Atlantic. But better steel was only part of the story. The other half was geometry. The Liberty ships had used square hatch openings because they were easy to cut. Unfortunately, those right angles acted as amplifiers for stress. When a wave bent the hull, the force at those corners could multiply 3 or 4 times. The Victory design replaced every sharp corner with smooth curves, which allowed stress to flow evenly around the openings. It seemed like a small cosmetic change, but it was a crucial one. And in a final, brilliant move, the designers introduced a radical concept: deliberate imperfection. At strategic points along the hull, they replaced welded seams with old-fashioned riveted joints. These acted like fire breaks in a forest. If a crack ever did start, it would lose its energy when it hit a riveted seam, stopping it before it became catastrophic. They had learned that true strength wasn't about perfect rigidity, but about forgiving failure. When the war ended in 1945, the shipyards fell silent. The great cranes stood motionless against the California sky. The Richmond yards had produced over 700 ships, a miracle of steel and sweat that helped turn the tide of history. But as peace returned, the people who had built that miracle, including Bessie Hamill, drifted back to their lives, mostly forgotten. She clocked out one last time in the summer of 1946. There was no ceremony, no photograph, no newspaper clipping. Her work, as far as the world was concerned, was done. How is it that such a critical contribution, one that saved countless lives and reshaped an entire industry, could be so completely overlooked? Was it because she was a woman in a man's world, or simply because history prefers to remember the famous names on the executive office door rather than the quiet worker on the floor? The Victory ships kept sailing, carrying grain to Europe under the Marshall Plan and supplies during the Cold War. Decades later, inspectors noted that their hulls still showed no catastrophic cracks. The method Bessie had discovered had outlived the war. In 1947, the American Welding Society published a new structural welding code. Buried in its technical language was a section on the balanced welding sequence, with diagrams that mirrored the ones Bessie had sketched in her notebook. It became mandatory for all critical structures, ships, bridges, and pipelines. The code never mentioned her name, but her influence is everywhere. When engineers designed the 800-mile Trans-Alaska Pipeline, they used stress relief procedures born in the Richmond yards. When the Golden Gate Bridge was retrofitted to withstand earthquakes, the teams followed the same center-outward principles. Every skyscraper, every offshore oil rig, every nuclear pressure vessel built in the decades since carries within it the ghost of a welder who refused to accept that's just how it's done. Bessie Hamill didn't invent a new technology. She gave the world something rarer, a new way of listening. The idea that the process itself can teach the designer, that the hand holding the torch knows something the blueprint never will. She lived a quiet life and passed away in 1987. Her obituary was 3 sentences long. It mentioned she had worked in the wartime shipyards. There was no hint that the welding code followed by every modern engineer carried her fingerprints. and yet her legacy endures, not in monuments, but in the things that don't break. Today, a few preserved Victory ships still float in harbors, museums of steel and memory. Most visitors never notice the weld seams running along their hulls, smooth, evenly spaced, and unbroken. But they tell a story, a quiet reminder that sometimes the greatest breakthroughs don't come from a flash of genius in a laboratory, but from the simple, steady courage to pay attention. The story of the breaking ships and the woman who fixed them is more than just a piece of history. It's a quiet lesson in humility. It reminds us that sometimes the most profound answers aren't found in complex equations or executive boardrooms, but in the hands-on wisdom of those who do the work. Bessie Hamill didn't have a degree in engineering, but she had something more valuable: the patience to observe and the courage to question. She listened to the steel, and in its groans and whispers she found a truth that had eluded all the experts. Her story asks us to look again at the world around us, at the bridges we cross and the buildings we enter, and to remember that they are held together not just by science, but by the unseen contributions of countless ordinary people who simply refused to ignore a problem. True progress is often a quiet collaboration, a chain of insights passed from one person to the next. Bessie's legacy isn't just in the ships that didn't break, but in the idea that every voice, no matter how small, has the power to make things whole again. It's a reminder that sometimes the most important thing we can do is slow down, listen carefully, and trust what our own eyes are telling us.